Earth and Venus appear almost identical. Placed side by side, the difference is difficult to see. Their rocky bodies are nearly the same size. Their masses are remarkably close. Their overall density tells the same story. If all we knew came from these measurements, there would be little reason to expect radically different worlds. Yet one carries oceans, weather, and life. The other hides beneath a permanent blanket of cloud. At its surface, the pressure is about 90 times greater than Earth's sea level atmosphere. Temperatures climb high enough to melt lead. Nothing about that landscape resembles the world suggested by its size. The contradiction arrives before the explanation. The measurements are not disputed. The mystery is, for generations, Venus was known as Earth's twin. The name was more than a metaphor. Its size, mass, and rocky composition all pointed toward a world that should have evolved in much the same way. That expectation is exactly what the evidence begins to break. The more precisely scientists compared the two planets, the less their modern histories made sense. The measurements themselves became part of the investigation. If two planets could begin this similarly, then whatever separated them happened later. Modern Venus offers the first visible clue. Hidden beneath its clouds lies a world unlike anything on Earth. The atmosphere is dense enough to crush unprotected spacecraft within hours. The surface is unimaginably hot. Yet those conditions cannot be explained by size, mass, or composition alone. Something fundamental changed after these planets began their histories. To understand that change, researchers reconstructed the earliest Venus they could justify from evidence rather than imagination. Climate models suggest that long ago, Venus may have possessed a massive inventory of water. Whether that water ever settled into long-lived oceans or remained mostly as a deep envelope of steam is still debated. That uncertainty remains. The possibility does not. The reconstruction is carefully labeled because it is exactly that. A reconstruction, not a photograph of the past. But it is enough to transform the investigation. The familiar image of Venus as a planet that was always doomed begins to weaken. In its place appears something far more unsettling. A world built astonishingly like Earth. A world whose history may once have followed the same path. Only now does the real question emerge. What disappeared? The search begins with an absence. Modern Venus is almost completely dry. No rivers cut across its surface. No oceans reflect sunlight back into space. Nothing visible suggests that water ever played an important role there. If that were the whole story, the investigation would end here. A planet closer to the Sun lost its water. Case closed. Instead, the atmosphere preserves evidence that the surface no longer can. High above the clouds, scientists measured something that should not have been there in such overwhelming amounts. Among the ordinary hydrogen atoms remained an unusually large concentration of a heavier form known as deuterium. At first glance, the difference seems insignificant. One isotope is only slightly heavier than the other. But on a planetary scale, that tiny difference becomes a permanent record. When sunlight breaks water molecules apart high in an atmosphere, the lighter hydrogen escapes into space more easily than the heavier deuterium. Given enough time, ordinary hydrogen gradually disappears while more of the heavier isotope remains behind. The atmosphere slowly remembers what the surface has forgotten. Measurements from separate space missions reach the same conclusion. Venus contains roughly 150 times the deuterium-to-hydrogen ratio found in Earth's oceans. That number is not simply another atmospheric statistic. It is a forensic fingerprint. It points toward the loss of an enormous amount of water. Not a puddle. Not scattered ice. A planetary water inventory far larger than what modern Venus could ever hold. The simplest explanation begins to fail. Perhaps the sun merely dried the planet over billions of years. If that were true, the atmosphere would not carry such a dramatic isotopic scar. Heat alone cannot explain why so much ordinary hydrogen vanished while its heavier counterpart remained. Something far more extensive happened. The water did not quietly disappear. It was dismantled molecule by molecule. Even here, the evidence demands restraint. The isotope measurements reveal how much water was lost. They do not reveal exactly what that water looked like. Some climate models suggest early Venus may have supported liquid oceans for a time. Others indicate the planet may have remained wrapped in dense seas before liquid seas could ever become stable. The debate continues. The measurement does not. Whatever form that ancient water took, it once existed in quantities great enough to leave a signature that survives billions of years later. The missing water returns, not as an ocean stretching across a young world, but as invisible chemistry suspended inside a hostile sky. An object that seemed gone forever has become the strongest evidence in the investigation. Now the question changes. Water was present. Water was lost. How could the very substance most closely associated with habitable worlds become part of the process that destroyed one? On Earth, water stabilizes a planet. It fills oceans that absorb heat. It forms clouds that reflect sunlight. It moves through rivers, glaciers, and rain, carrying energy from one place to another. It is so closely tied to habitability that it is easy to assume its presence always makes a world safer. That assumption works. Until Venus. The reconstruction begins with the planet carrying a massive inventory of water. Whether that water existed mainly as oceans or as a deep envelope of steam remains uncertain, but either possibility leads to the same critical moment. More energy from the nearby sun entered the system. At first, nothing catastrophic had to happen. More sunlight simply meant more evaporation. More water entered the atmosphere. That still sounds familiar. On Earth, evaporation is part of a balanced cycle. Water rises, clouds form, rain falls, and the system continually redistributes heat. The expectation is so deeply rooted that it becomes difficult to imagine the cycle failing. Then, the atmosphere itself began to change. Water vapor is not just water. It is also one of the most effective greenhouse gases known. Every additional layer of vapor trapped more of the planet's infrared heat. As temperatures climbed, even more water entered the atmosphere. More vapor trapped more heat. More heat produced more vapor. The cycle stopped regulating the climate. It began amplifying it. For a time, it might still have seemed reversible. A warmer planet should eventually radiate more energy back into space. That is how cooling normally works. But physics imposed a limit. As the atmosphere became increasingly saturated with water vapor, the amount of heat escaping into space could no longer keep pace with the energy arriving from the sun. Climate models describe this threshold as a physical ceiling on the planet's ability to cool itself. The escape route narrowed. The incoming energy did not. The familiar climate cycle transformed into a runaway greenhouse. From that point onward, the water inventory was no longer protecting the planet. It had become the engine driving its transformation. As temperatures continued to rise, more of that water reached the upper atmosphere, where intense ultraviolet sunlight broke each molecule apart. Hydrogen, the lightest element, drifted away into space. The heavier deuterium remained behind. The invisible fingerprint discovered earlier was being created in real time. The missing water had not simply vanished. It had first become the atmosphere. Then the atmosphere became the trap. Only afterward did the water itself begin to disappear. What remained was no longer a world slowly becoming warmer. It was a planet crossing into an entirely different physical state. The consequences of that transition still lie hidden beneath Venus's clouds. The surface has been waiting there ever since. The clouds reveal nothing. From orbit, Venus appears wrapped in an unbroken blanket of pale yellow cloud. Visible light cannot penetrate it. For centuries, the planet's surface remained hidden, leaving imagination to fill the space below. Reality turned out to be far stranger. Instead of cameras, researchers used radar. Powerful radio waves passed through the clouds, struck the ground, and returned to an orbiting spacecraft. Piece by piece, nearly the entire planet emerged from the darkness. The landscape that appeared was not simply hotter than Earth's. It belonged to a different world altogether. Endless volcanic plains stretched across the surface. Broad lava flows covered enormous regions. Strange circular mountains, known as pancake domes, rose from the plains where thick lava had once forced its way upward before hardening in the crushing atmosphere. Almost nowhere did the radar reveal the familiar signatures of flowing water. No winding river valleys. No coastlines. No sedimentary landscapes carved over millions of years. The missing water had left almost no visible trace behind. The atmosphere completed the picture. When Soviet landers briefly survived on the surface, they transmitted measurements directly from the ground. The pressure was about 90 times greater than Earth's at sea level. Standing there would be like descending nearly a kilometer beneath Earth's oceans, except the surrounding fluid would not be water. It would be carbon dioxide. The temperature approached 475 degrees Celsius, hot enough to melt lead. Yet the ground beneath those conditions was not an endless sea of glowing lava, as popular imagination often suggests. It was solid basalt, ancient volcanic rock resting beneath an atmosphere so dense that the horizon itself would appear dim through the thick carbon dioxide and filtered sunlight. Heat alone could never explain this landscape. Pressure alone could never explain it. Volcanoes alone could never explain it. The atmosphere, the missing water, the volcanic plains, and the chemistry now began to align. Each observation had once seemed independent. Each mission had answered a different question. Radar mapped the surface. Landers measured the pressure and temperature. Atmospheric probes analyzed the gases. Together, they no longer described separate mysteries. They described different parts of the same planetary history. The world beneath the clouds was no longer scenery. It had become evidence. Every plane of hardened basalt, every crushing layer of carbon dioxide, every trace left by ancient volcanism, each belonged to the same irreversible sequence that had begun long before the surface reached its present state. The investigation no longer asks what Venus looks like. It asks whether every surviving measurement can be assembled into one complete reconstruction. The reconstruction begins by placing every surviving piece of evidence on the same table. One set of measurements describes a rocky planet, almost indistinguishable from Earth in size. Another preserves the chemical fingerprint of an immense loss of water. Climate physics explains how a water-rich atmosphere can trap enough heat to prevent a planet from cooling. Radar reveals a dry volcanic surface hidden beneath permanent cloud. None of these observations contradict one another. They fit together with increasing precision. The sequence opens with the only world the evidence allows: a rocky planet remarkably similar to Earth. Models suggest it possessed a massive inventory of water. Whether that water collected in the long-lived oceans or remained primarily as dense atmospheric steam is still being investigated. That uncertainty remains inside the first chapter alone. Everything that follows becomes increasingly difficult to escape. Closer to the Sun. Venus received more incoming solar energy than Earth. The additional heating pushed more water into the atmosphere. As water vapor accumulated, it trapped even more heat. More trapped heat produced more evaporation. The atmosphere grew thicker with its own greenhouse gas until the planet reached the point where releasing that heat back into space became physically limited. The transition was no longer gradual. The climate had crossed a threshold. The water that once represented habitability became part of the mechanism driving the planet away from it. High above the atmosphere, ultraviolet sunlight broke those water molecules apart. Hydrogen escaped into space. The heavier deuterium accumulated. Billions of years later, spacecraft would measure that imbalance without ever witnessing the process itself. The chemistry preserved what the landscape could not. As the water inventory disappeared, another change became permanent. Without abundant water participating in long-term geological cycles, carbon dioxide was no longer removed and locked away in the same manner seen on Earth. Volcanic activity continued releasing the gas into the atmosphere, where it accumulated instead of being recycled. The atmosphere thickened. Surface temperatures climbed higher. The pressure increased. Each consequence reinforced the next. By the time radar mapped the surface, the sequence had already finished. The volcanic plains were no longer simply volcanic plains. They were the landscape left behind after the climate had settled into a new equilibrium. The crushing atmosphere was no longer an isolated curiosity. It was the surviving product of the same chain that had erased the ancient water inventory. The investigation tests the reconstruction one final time. Remove the isotope evidence, and the missing water becomes difficult to explain. Remove the greenhouse physics, and the atmosphere has no documented path to its present state. Remove the radar observations, and the final landscape loses its physical confirmation. Remove any one element, and the reconstruction weakens. Keep them together, and each independent observation strengthens the others. One uncertainty remains. Researchers continue to investigate whether Venus's earliest water spent long periods as liquid oceans or existed mainly within a dense steam atmosphere before the runaway greenhouse accelerated. That question is still active. It no longer changes the central reconstruction. However the water first existed, the evidence shows that it was lost. Its disappearance is written into the atmosphere. Its consequences are written across the surface. The separate discoveries no longer stand alone. They have become one planetary autopsy. Continue. Earth and Venus still appear almost identical when viewed from space. The measurements have not changed. Only their meaning has. The blue world returns one last time. Not as an image captured by a spacecraft. Not as a forgotten illustration from an old astronomy book. It returns only as the object the investigation has been following from the beginning. A world carrying a vast inventory of water. At first, that image represented similarity. A reason to believe Venus and Earth once belonged to the same familiar category. Then the water became evidence. Invisible chemistry preserved inside the atmosphere revealed that it had once existed in extraordinary quantities, even after every visible trace had vanished. Now it returns as absence. Nothing on the modern surface points toward ancient shorelines with certainty. No ocean reflects sunlight beneath the clouds. No river crosses the volcanic plains. Yet the missing water is present everywhere. It survives in the excess deuterium left behind after lighter hydrogen escaped into space. It survives in the atmosphere that no longer contains the water needed to interrupt its greenhouse trap. It survives in the volcanic landscape that developed under conditions no longer moderated by abundant water. The object itself has disappeared. Its evidence has not. Placed beside one another for the final time, Earth and Venus still resemble siblings. Their outlines remain almost interchangeable. Their mass, their size, their rocky composition. None of those measurements warned how differently their histories would unfold. The decisive changes are written elsewhere, in isotope ratios suspended high above the clouds, in climate physics that describes a threshold once crossed, in radar maps of a dry basaltic world hidden from ordinary view. Each record was gathered independently. Each survived its own tests. Together, they reconstruct a single transformation. Some details remain open to investigation. Researchers continue to examine whether early Venus held stable liquid oceans or whether much of its water remained as a global steam envelope before being lost. That uncertainty survives because the evidence allows it. The larger reconstruction survives with it. The water existed. The planet crossed irreversible physical thresholds. The atmosphere changed. The surface changed. The chemistry remembers. The clouds still conceal the ground from human eyes. The evidence no longer does.